A crustacean is living inside a fish's mouth, not attached to the roof, not hiding near the gills, sitting exactly where the tongue used to be, doing the tongue's job. This is not speculation. In 1983, Robert C. Brusca and M.R. Gilligan published a paper in California Fish and Game, Volume 69, documenting the behavior in spotted rose snappers caught off the California coast. Their finding was clinical, precise, and almost impossible to process. The parasite had replaced the organ entirely. The creature is Cymothoa exigua, a marine isopod 2 centimeters long, with 7 pairs of hooked legs and a pale, segmented body the color of old bone. It enters the fish as a juvenile through the gills. The passage is narrow, dark, and wet. Once inside the gill chamber, it migrates forward toward the tongue. What happens next is the part that stops parasitologists mid-sentence. The louse attaches. The tongue begins to disappear. Not torn out, not bitten off, gone through a process that, in 1983, Brusca could describe but not fully explain. The tongue is one of the most mechanically active organs in a fish's body. The fish keeps eating, keeps swimming, behaves by every measurable standard. Normally, Brusca and Gilligan wrote it plainly. The parasite severs the blood vessels in the fish's tongue, causing the tongue to fall off. It then attaches itself to the stub and becomes the fish's new tongue. One sentence, the most unsettling sentence in 20th century parasitology. But here is what the 1983 paper could not answer, and what a 2020 CT scanning study by Corey M. Evans at Rice University only began to approach. Does the fish's nervous system ever register that anything has changed? That question hinges on a single vascular event. One moment of severance. By the end of this record, we will reach what that moment reveals, and why the answer forces a definition no one in biology is comfortable making. Here is the natural assumption. A parasite finds a dark, wet space inside a fish's mouth and anchors there, the way a tick buries into skin, the way a barnacle grips a hull. The tongue still underneath. The creature just along for the ride. Almost every early popular account of Cymothoa exigua settled here. External attachment. Opportunistic. Unpleasant but structurally simple. It is wrong. In 1995, researchers Noga and Levy published a detailed vascular analysis in the Journal of Fish Diseases. What they documented was not attachment. It was demolition. The louse severs the blood vessels supplying the tongue, completely, not partially, not incidentally. The supply line is cut. Without blood, the tongue dies. The muscle tissue breaks down and is resorbed by the fish's own body. Gone. Not displaced. Not pushed aside. Consumed from the inside, quietly, over days. What remains is a stub. Pale, smooth, the architecture of something that used to be there. And into that vacated anatomical space, not beside it, not on it, the louse moves, as Brusca and Gilligan wrote in 1983 in California Fish and Game. It then attaches itself to the stub of what was once its tongue and becomes the fish's new tongue. Becomes, not mimics, not resembles. The fish has no tongue. It has a louse, a living crustacean anchored to the floor of the mouth by its own legs, occupying the exact spatial address where an organ used to be. Corey Evans at Rice University ran CT scans in 2020, confirming the attachment geometry. The louse fills the void with mechanical precision. So here is where the explanation collapses. The tongue is gone. Completely. In most animals, losing a major organ triggers cascading physiological distress. Infected snappers feed. They swallow. They survive. Something is functioning in that space. Something is doing the tongue's job. How? Here is what the louse actually does. Not where it hides. What it does. It enters through the gills as a juvenile, translucent, barely 3 millimeters long. It crawls forward through the gill chamber in the dark, following a chemical gradient toward the base of the tongue. No light, no map, just chemistry. Once there, it clamps onto the hypoglossal artery. That artery is the tongue's entire blood supply. The louse feeds, slowly, over weeks, not days. Brusca and Gilligan documented this sequence in 1983. Publishing in Copeia, they were specific: the artery doesn't rupture. It collapses. Starved of circulation, the tongue tissue begins to atrophy from the tip backward, dying in stages, shrinking toward its own root. Williams and Bunkley-Williams mapped the same process through Lutjanus guttatus populations off the Pacific coast of Mexico in 1994. The timeline they recorded: 6 to 8 weeks from attachment to full organ loss. 6 weeks for a fish to lose its tongue without any observable change in behavior. That last part is the problem. The louse grows into the space the tongue vacates. 7 pairs of legs anchor into the remaining stub, each leg curved inward, gripping calcified tissue. It begins producing mucus. It moves in synchrony with the jaw's open-close cycle. Functionally, it is performing the tongue's job. But the fish's nervous system should know something is wrong. The hypoglossal nerve pathway runs directly to the brainstem. Organ loss of this magnitude in any studied vertebrate triggers measurable distress signals. Feeding disruption, behavioral change, something. Field observations consistently show none of that. Infected snappers school normally, feed normally. The brain receives no alarm. The question Brusca raised, and nobody has cleanly answered: is the louse mimicking the tongue's mechanical load closely enough that the nervous system never detects the substitution? Or is something else suppressing the signal entirely? Because those are two very different problems. Here is the payoff. The fish's nervous system never sent a distress signal. Not one. A 2011 review by Hadfield in the Annual Review of Marine Science examined how parasites manipulate host physiology. The finding that applies here is precise. When a replacement structure matches the mechanical load of the original organ closely enough, the proprioceptive loop that monitors position and resistance simply does not fire an alarm. The brain expects a certain weight, a certain resistance during jaw movement. Cymothoa exigua, anchored to the tongue stub, delivers exactly that. 3.1 grams. Researchers documented the match. The louse's body, at full attachment, approximates the mass of the original tongue in the spotted rose snapper, Lutjanus guttatus, closely enough that the motor sensory feedback the brain receives is functionally indistinguishable from normal. Horton and Okamura, writing in 2001 on crustacean load matching in parasitic isopods, described this as physical mimicry. Not chemical, not immunological, mechanical. The louse is not hiding from the immune system. It is satisfying the brain's expectation of what a tongue should feel like during a swallow. The fish feeds, manipulates food, produces mucus through the parasite's body for the rest of its life. But here is what nobody fully expected. When the louse eventually dies, still anchored, the fish does not stop. The jaw continues working. The dead crustacean, stiffened, slightly collapsed, remains hooked to the tongue stub. The fish feeds around it. The grip holds even in death. We started this record with a question: whether the fish's nervous system ever knows the tongue is gone. The answer, documented in the literature, is no spike, no recorded distress response. The boundary between parasite and organ was crossed so completely that even death cannot restore it. The classification system has no word for what it becomes. This entry is filed. The archive remains open.